Welcome to Ready to Derive. In this video, we will take a break from the intense algebraic manipulation required to find the equation of the derivative of a function and instead adopt a more holistic and intuitive perspective. In particular, we will learn how to approximate values of a derivative from both tables and graphs. As always, there will be interesting context and plenty of examples along the way. So without further ado, let's begin. So let's begin by practicing estimating derivatives from a table of values. And we'll recall this context. We've seen this before, the Bay of Fundy in Canada. It's renowned for having the world's largest tidal variations. And this table here shows the height of the tide at 1 hour intervals from midnight to 12 p.m. And the Bay of Fundy really is spectacular. It's a beautiful place to visit. You should check it out sometime. Here's a picture I took a while back at low tide, and as you can see, the boats, they're not going anywhere. So we are going to estimate the instantaneous rate at which the height of the tide is changing at the following times using the table. And so if we look at let's look at time t equals 2 hours, we notice that, well, we have the height of the tide then, it's 5.5 meters. But we can't really tell what the rate of change is right there. So what we do is we go to the nearest available time values, so 1 a.m. and at 3 a.m., and we use those heights to kind of, approximate it. So how would we go about this? Let's see. So let's recall up. What we're really going to do is to approximate h prime 2, h prime being the rate at which the height is changing, i.e. the derivative. To work that out, we are going to need to find the height at 3 hours, at 1 hour, and then subtract the difference. In effect, we're finding the average rate of change over that interval and hoping it's pretty close. So at 3, let's just highlight again, we take 7.1, that's the height at 3 hours, at 1 hour. After midnight, it's 4.1. The time elapsed is 2, and that works out to be 1.5 meters per hour. That's the rate at which we approximate that it's increasing right at that moment. And again, remember this approximation, even though I put equals after this point, the approximation is what's really true. But this expression here, of course, is equal to this expression, which is equal to that. But overall, let me just clarify that here, h prime 2 is approximately 1.5 meters per hour. So now let's look at, let's see, now we want to estimate h prime at 5.5. Now 5.5, oh, that is in between 5 and 6, so that's 5:30 a.m. And so we take the nearest available values. So let's see, we know the height at 5 a.m. and at 6 a.m. And so we just use those to work out the value at 5.5. So let's see, we'll take the 6 minus 5 over 6 minus 5. And that is equal to, oh, how interesting, 9.1 minus 9.1 over 1, which is basically saying that it's 0. So we are estimating, well, see, if you notice, the values don't change. Look, 9.1, 9.1. So even though we know that something's happened in between, that's really all we can do. That's our best guess at what the rate of change is of the height of tide at that time. Okay, and so finally, let's look at 9.5 just for one more practice problem. So we know now 9.5 is there, so we have to take the average of those heights. So the height at 10 is, so the height of 10 minus the height of 9 over 10 minus 9, which is equal to 4.6 minus 6 over 1, so I don't really need that, which is equal to negative 1.4 meters per hour. So let's look at a visual representation of the calculations we made in the previous slide. So here's a graph of the heights versus time and made on Desmos. And we can see that it forms a beautiful function. It's the shape we will talk about in the next slide. But we know height is continuous because you can't get from one height to the other without passing all the other heights in between. So I'm going to kind of connect the dots and make a continuous function. Right, and so the first calculation we made was the instantaneous rate of change of the height at 2 a.m., which is right here. Actually, use red for contrast. And in doing that, we were actually working out the average rate of change over the interval 1 to 3, which was the slope of the secant line. And we can see that the slope of the secant line is the slope of that is very close to the slope of the tangent line there, which would give the exact value of h prime 2. So pretty good estimate. And let's go to the next one, 5.5 or 5:30 a.m. That was here. We got 0 because, of course, the slope of the secant line there is 0. And we can also see, again, a very good estimate to the slope of the tangent line if we could find it at that point. Finally, at 9.5, which is at 9:30 a.m., we see that we got negative 1.4, so the tide is going out. That's the slope of that secant line. Once again, that seems to be very close to the slope of the tangent line if we could work it out at that point. So in the next slide, I'm going to show you how we could, in fact, generate a function for this graph, and how powerful that could be combined with calculus. So on this slide, we're going to see how well we did with our estimates of the instantaneous rate of change of the tides. So here is the data in a table. I imported it into TI-84, and I created this graph. I graphed the data points, and then I modeled it using a method called regression. And in fact, the regression that I tried was a sine regression. You could have done a cosine or a sine. You can recognize that this modeled by one of those, because tides naturally, they have a period to them, about just over 12 hours. Every 12 hours, you have a low tide again. So no surprise that the model would be a sine or cosine. So this is what I generated, and then I took the derivative of that. We don't yet have the ability to do this in a easy enough manner. We could use a limit definition of a derivative. It would take forever. So we'll hold off on that. You'll just have to trust me. I took the derivative and evaluated it at t equals 2. So t equals 2 was right there. So I got 1.47. So that would mean that's the slope of the tangent line right there. And let's compare. What we got before was 1.5. So it was a pretty close estimate. And then I repeated it at 5.5, which remember was between two data points. So the slope of the tangent line, I got to be 0.09, and we got before 0. So again, pretty close. Finally, at 9.5, which was between here and here, the tangent line to this model would be negative 1.43, and before our estimate was negative 1.4. So our estimates are pretty close to those we obtained from this model. So let's pause for a moment to summarize what we've achieved so far. So if we'd like to estimate the value of a derivative of a function at x equals c, say, you first of all identify the smallest interval, ab, that contains c. And it's important that obviously you know the value of the function at a and at b. And then you just find the average rate of change over this interval. And not forgetting to include the approximation sign, you generate this formula. So as we can see on the right-hand side, this is the average rate of change. I'll just put ROC. And on this side is the value we don't know for sure, but we're hoping to estimate is the instantaneous rate of change. So we're going to practice using that formula one more time, but I've changed up some notation here. So this table is generic. There's no context here. So we're just estimating derivative values. In the previous example, we used function notation. Now, the nice thing about function notation, if you want to find the derivative at 1, you would just write f prime 1. But we don't have function notation, so you have to learn another way to do this. And so when we're using dy by dx, the convention is we put this vertical line segment and we say find the derivative at x equals 1, and we write the x equals 1 down there. So remember, it's approximate. And remember that we have to, here at 1, we have to find the interval that contains 1 and find the average rate of change over that interval. So that would be 3 minus 5 over 2 minus 0. And that would equal to 2 over 2. And that's, well, sorry, negative 2 over 2, which is negative 1. And then we're going to repeat. So dy by dx now at x equals 8 is approximately, let's go and find those values. Here we go. Let's use different colors. So 8, x equals 8 is right there. So this interval will work nicely. And if we use that, we would do 8 minus 4, that's the change in y, over 10 minus 6, 4 over 4. So the instantaneous rate of change there is approximately 1. I'm going to make a shift now to estimating derivatives from a graph. So this context should be familiar. A ball is thrown up in the air with an initial velocity of 60 feet per second. We've seen this in previous videos. And the ball's height in feet after t seconds is shown by the red function. So we would like to estimate the instantaneous velocity of the ball at t equals 1 second. So instead of finding an interval that contains 1 and sort of using the function to estimate this, so we're not actually going to find the slope of the secant line, we are going straight to the tangent line. And instead, we are going to pick 2 points on the tangent line that are, easy to read. So like this point here, P, let's call this P, that looks pretty good. And so does this point, it goes through a grid line Q. And so the coordinates of P is 0.5, comma 30, and the coordinates of Q is 1.5, comma 58. And so if we like the instantaneous velocity of the ball, well, now it's still going to be approximate, right? Because this tangent line might not be perfectly drawn, but it's going to be the change in y, so 58 minus 30 over the change in x, 1.5 minus 0.5, and that leaves us with 28. So 28 feet per second. And if you do recall this context from a previous video, that is exactly what we got by using the limit definition of a derivative to find the instantaneous velocity at t equals 1. So the remainder of this video is devoted to learning how to sketch a derivative function. Instead of getting caught up in the algebra of generating the equation of the derivative function, we're just going to take a more holistic perspective. So we're going to start off with a linear function. And we're going to do this by estimating the slope of tangent lines. Now, for a linear function, that's kind of an easy task. Let's look at x equals 1. At x equals 1, the slope of the tangent line, well, it looks like the slope of the tangent line would just be the slope of the line itself, which seems to be, if I negative down 1 over 2, it's negative a half. So I'm going to put a mark there to indicate that it's negative a half. And wherever I go, so if I go to x when x is 0, well, that's negative a half as well. Well, of course, a linear function has a constant slope, so it looks like the equation or the form of the derivative of a linear function is also linear, but a particular type of linear. This is obviously a constant function. So let's have a look at that. So when you have a linear function, whether it be 3x minus 5 or y equals x, the derivative is always a constant function because of the slope of a linear function is constant. So now we're going to repeat this process, but for a quadratic function. So here's a general quadratic function, and now it's not so easy. The linear function was much easier to graph the derivative. So I'm going to give you a couple of pointers here. The best place to look is always to find where there's a horizontal tangent line, because we know that a horizontal tangent line means there's a slope of 0. So if we look at x equals 1, so at x equals 1 right here, we see that at that point, we're pretty confident that the tangent line is horizontal and therefore that the slope is 0. So I am going to put a little mark, because remember, graphing the derivative now. So at x equals 1, the derivative would be 0. Now, the next best points to look for is wherever the tangent line looks to have a slope of about 1. So I'm looking over here at x equals 2, because I see that if I kind of, well, secant line or the tangent line look pretty similar. I see a little right triangle that has, it looks like it's over 2, up 2. So I'm thinking that the slope there is 1. So I'll put a little note here, f prime equals 1, f prime equals 0 there. So I'm going to go up to 1, record the slope. If by the symmetry of this situation, it looks, I could also say here at x equals 0, it looks like the slope is, in this case, -1. So I'm going to put an x down there. Now, you could continue on. If I look at, let's see, at this point here at x equals 1.5, it looks like it's over 2, up 1. Well, I sort of knew where I was going now, that this was going to result in a linear function. The derivative was going to be linear. When we're estimating it like this, your graph may not be a perfect rendition, but we get the idea that the derivative is indeed a linear function. So here we go again, this time for a cubic function. So as before, we begin by finding horizontal tangent lines. There appears to be one here, so f prime is 0. Put a little x to record that slope, and also at -1, f prime equals 0. There we go. Those are the easiest. The next thing to do is to look for slopes. I've said slopes of 1 or -1 will do. And if I look right at x equals 0, right here, it really does look like the slope is -1 down to right 2. So I'll put an x here. And then searching for another slope of 1. This looks good at x equals 1.5. I have another little isosceles right triangle, so the slope appears to be 1 there. And by the symmetry, let's see, I would think that the slope is 1 here as well. Let's see, at -1.5. So I think you'll recognize that the derivative of a cubic is a quadratic. Notice here that I used, instead of using f of x equals, I used y for the cubic, so therefore dy by dx is the correct notation for its derivative. And if I just sketch this, so hopefully you're noticing now that the derivative of polynomial functions seems to always be 1 degree less than the polynomial itself. So for our last example, we will look at the derivative of sine x. This is a bit of a spoiler alert, because the derivative is going to be a function which you may not have realized was so intimately related to sine x. But nonetheless, it's a fun preview. It doesn't prove the result. We'll actually do that in a later video. So we begin by finding horizontal tangent lines, because at those points we know that the slope is 0. So we are recording the slope at these points as being 0. And then we look for where the slopes are 1 or -1. It looks like here I have a nice isosceles right triangle. So the slope is 1 at x equals 0. And it appears that at actually wherever there's an x-intercept, we have a 1 or -1 slope. So there and here, -1. And at the far reaches, it appears that the slope is 1 also. And hopefully you see that as we connect the points, I'm not sure why I'm using yellow, but it's maybe because it's such an important result. As we connect the points, we see that a cosine graph is generated. So the derivative is indeed the derivative of sine x is indeed cosine x. Notice that I changed the notation slightly. Instead of writing dy by dx, I used y prime. In the same way that if the function is f, the derivative is f prime, you can also use y prime as an abbreviation. And the most important takeaway from this activity for the last few slides is that think of the derivative function as that function which records the slope at every point of its parent function. It's like a very important intuitive way to look at derivatives, especially when you get caught up in the weeds of calculating derivatives. It's nice to take a step back and kind of have an appreciation of what that function represents. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.